Again, in this video we're going to discuss cis versus trans isomerism, as well as a new way to name molecules, E versus Z. So let's start with cis versus trans. We've already gone over a couple of examples with cis molecules and trans molecules, but let's take this a bit further. So I'm going to draw a molecule and you're going to name this molecule. Okay, so try to name this molecule. If you need to pause the video, you can, and when you come back, we'll go over it together. Okay, so let's name this molecule. Remember, if you have a ring in your molecule, that will be the parent chain. So how many carbons are in the ring? 6. And because it is a ring, we're going to add cyclo in front of hexane. So remember, hexane tells us that we have 6 carbons that are all singly bonded to each other, and then cyclo tells us that they're all in a ring. Okay, so now we have to name the substituents. So let's see, we have 2 methyl groups. One is at the top, one is at the bottom. So I guess it doesn't really matter which way we number this ring, right? We could start from the top or the bottom. Either way, we end up with a methyl group on carbon 1 and a methyl group on carbon 4. So how would we then name those? So 1, 4 dash dimethyl cyclohexane. Okay, great. So we have a name here, but there's another molecule that has the same name. So this molecule on the right also can be called 1,4-dimethyl cyclohexane. We have 2 methyl groups, one on carbon 1 and one on carbon 4. So how do we tell these 2 molecules apart? Well, you'll notice that on the top, on carbon 1, the methyl groups are both dashed, so they're, in a wedge position, so they're both pointing up towards us. But then on the bottom, we have one methyl group in a wedge position, and then on the other molecule, the methyl group is in a dashed position. So when something's in a dash position, it's pointing away from us into the plane of the paper. So that means we need a way to differentiate these 2. So what if we assign R and S? Because we have used that before. So let's see if we can find any stereocenters. So look at these 2 molecules and see if you can find stereocenters. Okay, so it kind of looks like we have a stereocenter at the top here, right, where I put the red star. All right, so that carbon, carbon 1, let's focus on that. So it's bonded to a methyl group up above. There's a hydrogen that's hiding in the back, so it's also bonded to a hydrogen there. Then it's bonded to 2 carbons. So we need to figure out which one gets first priority, right? So let's see, carbon 2 is bonded to carbon 3. And that looks pretty similar to the other side too, right? Okay, so they're tied again. And then carbon 3 is bonded to carbon 4, but so is this other carbon on the opposite side. And then carbon 4 is bonded to a methyl group. So we actually have the same connectivity on both sides. So that's actually not a stereocenter. Because carbon 1 is bonded to 2 of the same groups. So we just showed that whichever way we go down the ring, we end up back at carbon 4, right? So carbon 1 is actually not bonded to 4 different groups. So I'm going to erase that asterisk that I drew earlier because that is not a stereocenter. Same with the carbon down below, carbon 4. It might look like a stereocenter, but if we track up the ring, we can see that in fact carbon 4 is not bonded to 4 different groups. Now looking at our other molecule on the right-hand side, that's the same case. So even though we have a wedge position at carbon 4 for that methyl group, that doesn't really make a difference. We're more interested in the chain of carbons going around the ring. So those also are not stereocenters. Okay, so we can't assign R or S to these molecules. So the only other way that we could really tell these molecules apart is by using cis and trans. So let's kind of write down a summary here. So there were no stereocenters on either of these molecules, which means that we can't assign R or S. So the only other way to tell someone that these are different molecules is to use cis and trans. Now, you might recall from before that cis means that groups are on the same side of a molecule. So looking at our molecule on the left-hand side, we have 2 methyl groups that are both wedges. So they are both pointing up. So that is a cis molecule. And then on the right-hand side, we have a molecule where one methyl group is pointing up, one is pointing down. So those are opposite each other on the molecule. So that would be trans. All right, so the name for the molecule on the left is actually cis-14-dimethylcyclohexane. And then the molecule on the right, that is named trans-14-dimethylcyclohexane. So again, cis means that your substituents are on the same side, and let's see, I'll use blue for trans. That means that your groups are on opposite sides. All right. Now, let's also think about these isomers in terms of constitutional isomers, enantiomers, or diastereomers. So looking at these 2 molecules, are they constitutional isomers? Are they enantiomers? Or are they diastereomers? And you can pause the video if you would like to think about it for a minute. Okay, so let's think about, are they constitutional isomers? So remember, constitutional isomers have the same molecular formula, but they're connected in different ways. But looking at these 2 molecules, everything is connected in the same way. We have a methyl group at carbon 1, a methyl group at carbon 4, and a 6-membered ring. So there's really no difference in the connectivity there. So that just leaves us with enantiomers versus diastereomers. Now remember, enantiomers are non-superimposable mirror images, but enantiomers are also typically chiral, so they have stereocenters. Now, looking at these two molecules, we already said that they don't have stereocenters. Stereomers. I'm not sure where that word came from. So these two are not enantiomers because they do not have stereocenters. However, they are diastereomers. So they're diastereomers because they have the same molecular formula, but a different 3D layout. Oh, I'm writing in highlighter. There we go. So remember, if you go back to the definition for diastereomers, they are not mirror images. And looking at these two molecules, they are in fact not mirror images because, again, one has two wedges, the other one has a wedge and a dash. They have the same connectivity, that is true, but they are different in their three-dimensional layout, and that has to do with the wedges versus the wedge and the dash. So they are diastereomers. Okay, so we've talked about these two molecules enough. Let's go to another example. So in this example, we're going to look at two molecules again. So this first molecule, I believe we've seen before. And we're going to compare this to another molecule. Okay, so the first molecule, bromine and chlorine are both wedges. And in the second molecule, bromine and chlorine are both dashes. So I would like you to try to name these two molecules. And then when you're done, you can unpause the video and we'll go over it together. Okay, so let's name these two molecules. So let's start with the one on the left. So again, we have cyclohexane. And then we have to name the substituents in front. So let's see. We have bromine and chlorine. Bromine comes first alphabetically, so we're going to give that carbon 1. And then chlorine comes next, so that carbon that it's attached to will be carbon 2. Okay, so we have 1-bromo-2-chlorocyclohexane. But how do we say that this is different from the molecule on the right? That one is also 1-bromo-2-chlorocyclohexane. Okay, so the first one on the left, both bromine and chlorine are in wedge positions. So they're both facing in the same direction. So we could call that cis 1-bromo 2-chlorocyclohexane, right? Okay, so now let's look at the other molecule. Bromine and chlorine are both dashed. So they're also both pointing in the same direction, right? So that would also be cis, which, okay, there's no way we can really tell these two apart. Are they identical molecules? So if you try to rotate the second molecule, does it match the first one? Well, let's see. Let's try to rotate that molecule so that it is in a similar position to the first molecule. So let's just rotate it like a piece of paper. We're flipping it over. So if we flip that molecule over, bromine will be in a wedge position. So it'll be pointing up this time. Okay, that's promising. But chlorine will be over to the left of bromine. So it's no longer to the right of bromine. Now let's try to match up bromine and chlorine with the first molecule. So what if we just kind of turn this clockwise? So now chlorine will be on top. Bromine is off to the right. Okay, that doesn't match our original molecule either. So they are not identical. Okay, so we can't name these molecules using cis and trans. We have to find some other way to show that they're different. Okay, so we cannot use cis and trans in this example. So the only other way to tell these two apart is to use R and S. So let's see if we can find stereocenters. All right, so let's try to find some stereocenters here so that we can actually tell these two molecules apart. So we can't use cis or trans in this case, so we have to use R and S. All right, so I already see a stereocenter at carbon 1, and then I also see one at carbon 2, and that will be true for both of these molecules. And then I would like you to pause the video and assign R or S to these stereocenters, and when you unpause the video, we'll go over it together. Okay, so let's start with carbon 1 on the first molecule on the left. So that's bonded to bromine up above, and then a carbon and a carbon, as well as a hydrogen in the back. So let's prioritize our substituents here, or our different groups. So what has the highest mass? Bromine, carbon, or hydrogen? Bromine, so that would get number 1. Next would be carbon, but we have 2 carbons, so we have to figure out which carbon has higher priority, the one on the left or the one on the right. The one on the right, because it's bonded to heavier atoms like chlorine. So that gets priority 2, the other carbon gets priority 3, and then hydrogen is in the back, so we don't worry about it. That's our lowest priority atom. Okay, so if we draw a circle from 1 to 2 to 3, is that pointing in a clockwise direction or a counterclockwise direction? A clockwise direction, so that will be R or S? R. Great. Okay, so now let's go to the second stereocenter and let's figure out whether that is R or S. So that carbon that I'm pointing to with the blue arrow is bonded to chlorine, and then a carbon on the left, a carbon on the right, and a hydrogen in the back. So what has highest priority? Chlorine. And then next is carbon, but we have to figure out if the carbon on the left has higher priority or if the carbon on the right has higher priority. So which one would have higher priority? The carbon on the left, because it's bonded to heavier atoms, like bromine. All right, so we have 1, 2, and 3, and then hydrogen is our lowest priority atom, but it's in the back, so that's fine. So now if we draw a circle from 1 to 2 to 3, will that be R or S? S. So the circle that we would draw going from 1 to 2 to 3 is going in a counterclockwise direction. So that is S. Now, the great thing about this is that we just figured out that if bromine is in a wedge position on this molecule, it's in an R configuration. Now, looking at our other molecule on the right, bromine is in a dashed position, so that must be the opposite configuration, S. Similarly, chlorine on our first molecule is in the S position when it's in a wedge position. So that must mean that when it's in a dashed position, it's actually R. And really, we're talking about these stereocenters. We're not really talking about bromine and chlorine, but you get the idea. Okay, so looking at the naming for these two molecules, we again can't use cis or trans because we end up with exactly the same name, but you can see that these are two different molecules. We have RS for the first molecule and SR for the second molecule. So that means that we need to name these slightly differently. Okay. So we would name this, let's see, 1R, 2S, dash 1 bromo, dash 2 chloro, cyclohexane. So that's for the molecule on the left. For the molecule on the right, we would name that 1S, 2R, dash 1 bromo, dash 2 dash chloro, cyclohexane. So while cis and trans are really useful most of the time, in this particular instance and in a few other instances, you can't use cis and trans. You have to use R and S. Just something to keep in mind. Okay, let's look at E versus Z designation for alkenes. So earlier we saw this example of diastereomers. So remember, these molecules are diastereomers, and that's because they have the same connectivity but different 3D layout. Oh, different, there we go. So one way that we could name these two molecules is trans versus cis. And we'll learn how to name alkenes in more detail later, but one way that we could tell these two apart is by adding trans or cis in front of the name. However, there's one more way that we could designate these alkenes. We could call the trans alkene E and the cis alkene Z. So E comes from the, I believe, German word entgegen. Z comes from the German word zusammen. So entgegen means opposite, zusammen means same. So if you have two groups like these carbons, and they're on opposite sides of a double bond, then you can say they're trans, or you can say that it's E for opposite or entgegen. And then on the other side, if you have two groups that are on the same side of a double bond, so they're both pointing up or both pointing down, then you can call that cis, or you can label it as Z for same or zusammen. And I kind of like that same is kind of in the term there. So zusammen, same, they're very similar. So that helps me to remember which one is Z and which one is E. All right, so let's look at another example of how we can use E and Z, because it does come in handy for other situations as well. All right, so let's look at a couple of molecules. So we're going to look at some alkenes again. Oh, whoops, I drew it wrong already. Bromine is supposed to be on the other side. Chlorine is supposed to be there. All right, and then on our other molecule, we're going to flip chlorine and fluorine, but hydrogen and bromine will stay where they are. All right, so both of these molecules look pretty similar, except chlorine and fluorine are flipped. So on the left, fluorine is above the double bond, but on the right, fluorine is below the double bond. So what we can do is draw a line between the middle here, and then we kind of have above versus below. All right, so can you assign cis or trans to these molecules? Not really, right? Because we have so many different groups bonded to these carbons. How are you supposed to know when it's cis versus when it's trans? Well, you can't. Instead, we're going to use E and Z. So, for instance, let's go back. Looking at the two alkenes up above, those are very clearly cis and trans because there's only two main groups that are coming off of the double bond. The others are hydrogens, which we're not showing because these are bond line structures. However, if you look at these two alkenes, there aren't just two main groups. There's three. We have fluorine, chlorine, and bromine. So there's really no way that you can assign cis or trans here, but you can still assign E and Z. So I'm going to tell you how to do that. So one, we're going to prioritize the substituents. Let's see, according to atomic number. But these substituents are attached to the same carbon. Okay, so for instance, let's look at the molecule on the left. So we're going to first prioritize the substituents bonded to the blue carbon, and then we'll prioritize the substituents bonded to the red carbon. And then we'll do the same for the molecule on the right. So for the alkene on the left, let's look at the blue carbon. It's bonded to fluorine and chlorine. Now, which one has the higher atomic mass, fluorine or chlorine? Chlorine. So that gets priority 1, fluorine gets priority 2. And now let's look at the red carbon. The red carbon is bonded to hydrogen and bromine. So which one would get higher priority? Bromine. It has the highest atomic number compared to hydrogen. All right, so now are the substituents or the highest priority substituents, are they on the same side or the opposite side from each other? They're on the same side. So this would be Z for zusammen or same. So our second rule here, if highest priority substituents, and I'm just going to abbreviate that there as subs. So if the highest priority substituents, are on the same side, that equals Z. Opposite equals E. Okay, so let's look at our other alkene, and we already prioritized everything, so let's just write that down. So chlorine has higher priority over fluorine because it has a higher atomic number. And then we already said that bromine has higher priority over hydrogen. So looking at the chlorine and the bromine, which are both highest priority, they're on opposite sides. So that means that this is E. So E and Z are really useful if you can't quite assign cis or trans because you have more than two groups that you can consider for that. So oftentimes you can just use E and Z instead of cis and trans, even if it's really obvious that something is cis or something is trans. You can still use E and Z and it might be easier. All right, now again, we're not going to focus on naming alkenes right now, but in the future we will definitely name alkenes, so this is something to keep in mind. But this is also really important when we're thinking about different isomers as well. Okay, so next time we're going to talk about how to purify and isolate stereoisomers because it's not always super easy. So I will see you in the next video.